right? And suppose the page size is fixed, let's say 4 kilobytes or 8 kilobytes. Then the number of objects you can store in a given page for the record is B. For data entry, that must be B prime, right? Where you calculate this using page size divided by record size, right? Of course, you take the floor of this, and this is equal to page size divided by data entry size. Equal to that. And obviously, you have this relationship that B prime will be much larger than B because the data entry size is much smaller than a given record size. Which means the number of pages you have here is n over B, where this is n over B prime. So that the relationship is going to be like that. Okay? Does that make sense? And this n over B prime is my value m here in this figure right here. Okay, number of leaf level pages you need to store those entries. One thing you do, of course, is to sort those data entries according to the sort key value they have. That's why, because of that, you see these pointers may cross over each other, right? Because the data entries are no longer in the same order, potentially no longer in the same order as those records are. Okay, and then recursively similar to build up the index level pages. Specifically, what you do is you take the smallest sort key value out of each page and make an index entry with that sort key value together with the page ID that value comes from. Right? So, for example, look at this index entry here. K prime 1 is the smallest search key value among all data entries from this page, and this pointer is nothing else but simply the page ID of page number 2. You may wonder, why don't we do it for the first leaf level page? The reason is, as I explained last time, for a given leaf level, for a given index page, you have a leftmost pointer to work with. So you don't have to do this for every leaf page. For example, for the first leaf level page, you have to produce an index entry for it. That leftmost pointer of that index page will be able to index that first leaf level page for you. And every roughly B prime number of them, you can skip doing this for a leaf level page. Why B prime? Assuming index entry are roughly the same size as data entry, so every B prime number of index entries go to a page. That's when you can skip one index entry for index leaf level page, because that's when you start a new index level page that will give you a leftmost pointer to index that immediate next leaf level page. So every B prime of index entry, you can skip one of this procedure, which is taking out the smallest search key value from the leaf level page and make a PID pointing back to that leaf level page. So every B prime number of them, you skip doing so. And suppose B prime stay the same for all levels, which is typically the case if your data entry and index entry are the same size. Then if you carry out this analysis, what happens is, if you go one level down, how many entries you going to have? Roughly you have this many index entries. Actually it's smaller than this. Why? Because you skip B prime, every B prime entries you skip producing every B prime number of leaf level pages you skip one index entry. Does that make sense? Every B prime number of leaf level pages, you actually skip producing an index entry for it because of that leftmost pointer effect. But roughly, with n over B prime number of leaf level pages, you will have roughly n over B prime number of index entries. Okay? Roughly. You follow me? And this number of index goes to how many pages? Well, if you assume index entry size is the same as data entry size, then the number of index entries a page can hold is also denoted by B prime. So that will go to this many index pages. And then you continue this process until you have only one page left. That is your root page of your tree. Okay? So that's this procedure. And this is what a specific tree looks like. And this structure is static, right? So as good as it is a static data structure. Which means if you have insertion and deletion, that may lead to this effect called overflow pages. So overflow pages, right? So suppose you have insertion of a particular search key value. It has to go into that place because search keys, the data entries need to be sorted with respect to all the search key values. And there's no space on that page left. So you have to introduce an overflow page to accommodate that new data entries coming into that place. That's why you see these overflow pages over there. Okay? And as you can imagine, if you keep doing this for a while, this overflow chain becomes too long, then this indexing structure is no longer useful because you end up doing expensive linear scans through a very long overflow chain. Structure is not going to be efficient anymore. Okay? But in the basic setup, by the way, this process of building indexing structure, a tree indexing structure out of your records is what we call bottom-up bar coding. Okay. Why is it called bar coding? Well, because you are not inserting entries one by one. You have all the entries you want to have in the tree, and you build the tree for them in one round, rather than inserting entries one by one. Right? So that's why it's called bar coding. So bar coding, you should expect no overflow, obviously, because you control. You have a control over this value B prime. You will never have overflow happening in your construction. By the way, B prime is the maximum number of entries you can fit into a given page. You don't have to do B prime. You can use some value x that's less than B prime. By doing that, you actually leave some space in any given page to cater for future insertions into that page, so that you don't end up with overflow pages all the time. Does that make sense? Method of bar coding, which is you can control, this is what we call the utilization ratio of your tree. Basically, maximum you can hold B prime entries, but you are not using all B prime capacity. You are using something that's smaller than that. That gives you a ratio between 0 and 1. And as part of the bar coding process, you can control this ratio, which basically adjusts the trade-off between the size of your tree. Smaller utilization ratio means potentially your tree becomes bigger because you're holding less number of entries per page. So you have more pages in the leaf level. This translates to more levels in the tree. Okay, but at the same time, the benefit of using a smaller utilization ratio is that you can cater for future insertions without worrying about getting overflow easily. Okay, so that's a trade-off you have to consider. Now, this is an example where B prime equal to 2, right? Obviously, in practice, B prime is a number much larger than 2. This is only shown for illustration purposes. Okay? And when you lay out these pages, keep in mind, all of these are nothing else but pages, right? Pages. They're just index pages and leaf level pages. Conceptually, they're organized as a tree structure, but when you lay them back to disk, you have to define an order to place them back to disk, right? So typically in a database management system, an index is stored back to disk in this fashion, where you have your data pages first. So this is all your data pages, which is this guy right here. Okay, this guy right here. Index pages. Then you have your overflow pages. Index pages include both leaf level pages and index level pages. And typically it's stored level by level, meaning you start with all the leaf level pages, sequentially store them, then you go to the next level, sequentially store all of them, then you go to the next level, so on and so forth. The last page is the root page of your tree. Okay? And then when you have future insertion, deletion coming along, then you may introduce overflow pages, right? These guys. Obviously, one option will be to insert these pages in place, meaning, come back here, suppose this page is supposed to after it to make a space for it, but that becomes really expensive if you think about it, right? Because then you're basically reading a lot of pages and writing back them to disk to make space for this new overflow page, which is very expensive. So typically they don't do that. Rather, they introduce what we call an overflow page region and insert those overflow pages here. The benefit of this is very cheap, right? So you don't have to do these expensive reading and writing operations of many pages. But the downside is you destroy that locality, right? So by locality, what I mean is, suppose you are doing a range search. What I translate to is a sequential scan of leaf level pages. If you store those leaf level pages sequentially on disk, that translates to sequential IOs. But once you have these overflow pages organized in this fashion, you no longer have nice sequential IO all the time. Occasionally you have to do random IO. You have to do some sequential scan here, then you jump here to the overflow region to get your overflow pages, because you need to read them in order for range search, right? Then you come back to the index page region and continue the scanning operation. Okay? So that's the trade-off between the two. Okay? Here, I will skip this example because it's fairly straightforward. You can check out this example yourself. Okay? Next, I'm going to introduce the B plus tree. By the way, the structure we talked about is called ISAM. It's essentially a static version of B plus tree. Right? Next, I'm going to talk about the dynamic version of B plus tree that get rid of these expensive overflow chains by reorganizing the tree dynamically over time. So here is the detail. Okay. So the structure of B plus tree is the same as the structure we just talked about. You have data pages in your data file. You have data entries in leaf level pages and a bunch of index entries in organizing a tree structure in index pages. So the structure looks identical to the structure we just talked about. The only difference is B plus tree doesn't allow you to introduce these overflow pages like this. Rather, when this happens, you have to do dynamic reorganization of your tree such that the tree is balanced. So if you guys have taken a data structure or algorithm class, they should have explained by saying a tree is balanced. Right? Can someone explain to me what this means when I say tree is balanced? Does anyone know what that means?
I think
Michael?
it's just that the height of the tree is pretty consistent like at each subtree.
Yeah, the height of the tree is pretty consistent. Actually, the stronger requirement than pretty consistent. The precise definition is starting from the root of the tree. No matter which path you are looking at, a path means a complete path from a root node to any leaf level node. Any such path must have the same length, same height. That's called. So a tree with overflow chain obviously is no longer balanced because the length from this node to this node is 4, but the length from this node to this node is only 3. When you consider the distance between any leaf level node to the root level node. So it's no longer balanced. So the objective of B+ tree, a dynamic insertion deletion, is to ensure that your tree is balanced all the time, which essentially is equivalent to saying I don't want overflow pages. Okay? So how do we do that? So the structure is the same as before, so we skip this. So here is the example. Before the dynamic insertion deletion, I show you some simple examples. So if my objective is to find the data entry with search key value 28, I will load this page, come down here, and 28 is between 27 and 30. I will come down here and try to find it over this page. But if it's not there, I can safely claim that the database doesn't contain the value 28. So if I want to find all value greater than 15, what I will do is I load this page. I come here, then it's greater than 13, so I'll come here. Then I simply do a sequential scan in the leaf level pages. So now all you have to do is 1, 2, 3, 4, 5, 6. But keep in mind, this 1, 2, 3 are random IOs. The remaining 1, 2, 3 IOs are sequential IOs, given the way we store these pages back to the disk. Does that make sense? And typically, that's another observation I would like to mention, is that typically the first few levels of the tree, like first 2 or 3 levels of the tree, are cached in main memory. Why? Because you don't have that many pages in the tree anyway, in the first few levels. So caching them in main memory will not cost you a lot of space, you buffer space. So we will basically cache them all the time, meaning pin them all the time. A page is cached in buffer all the time. Very simple. You make the pin count never decrement back to 0. That way, it's never a candidate for replacement. So it will stay in your buffer. And that is something we call you pin the page. You pin the page. Right? You pin the page. That basically means keep the pin count above 0. Don't let it decrement back to 0. So that it never becomes a candidate for replacement. So when that happens, the number of IOs for this operation, if you think about it, there are no IO for this page, no IO for this page, because they are all pinned in your buffer. You only pay IO when you're going down to the leaf level. That's 1 IO, that's a random IO. But from there onwards, these are all sequential IOs. So this becomes really, really efficient for range queries. Okay? So that's the reason why. Now let's do some simple analysis of this B+ tree, right? So suppose your page size is, actually I have done this analysis here already, right? So if you just carry on this analysis, which is essentially what I have on the slides, the only difference is I materialize the analysis using some specific values. For example, I tell you the data entry size is 8 bytes, right? The search key value is 4 bytes. The record ID, I view that as a pointer of another 4 bytes, so total size is 6 bytes. Otherwise, this analysis here is exactly the same as what I have done in the whiteboard. In the blackboard right here. Okay. So if you continue this analysis, so for example, y, I get this value right here. The reason is you have n records that give you n data entries, and your page size is p. So b prime is p over 8. So that's your b prime. Right? So the number of leaf level pages is essentially this value. Right? So that's how you get the number over there. Does that make sense? Okay. And you continue this analysis. Suppose I use n prime to denote this analysis. I'm using n prime here. I use n prime to denote the number of leaf level pages. So that's what n prime stands for. Then you continue this analysis, you will get, so here I use, instead of b prime, I let f equal to b prime. F is what we call the found. Actually, f is not b prime. F is the value of x. The actual number of data entries you place into a page, either at leaf level or index level. And we know f must be a value less than or equal to b prime, the maximum capacity of a page, right? So I use f to denote this value, which is the x I mentioned earlier. And why I use f for this, because this is something called the fan out of your tree. The fan out of your tree. How many children nodes you can index given a particular page, given a particular index based on leaf level page. So if that's the case, I have n prime pages in the leaf level. How many pages I have in the level above? I will have n prime over f pages in the level above, then n prime over f squared, n prime over f cubed, until I have only one page root level. That's my root level. The question is, how long or how high this tree is, right? If you do a simple math, this translates to, you are trying to solve this equation, n over f prime x must equal to 1, that x is the height of your tree. So we translate to x equal to log fan out n prime, where n prime is number of leaf level pages, f is your fan out. Does that make sense? Of course, you take the ceiling of this, because you make sure that it reduces to just one page. So you have to take the ceiling of that. However, in this calculation, the height of the tree doesn't include the leaf level page itself. The leaf level itself. So if you want to be precise, you can plus 1 to it to counter for this level right here, which is, you can view this as n prime over f to the power of 0, meaning you start counting the level from level 0 instead of level 1. So in the literature, when people talk about B plus tree, the height of B plus tree, this is not it's not a consistent definition, in the sense that some people refer to the height of tree without counting the leaf level, while some others do count. Does that make sense? And depending on which conversion you are using, you either plus 1 to this formula here, or you don't do that plus 1. Okay? So you have to, in your homework, when I ask for the height of the tree, I give that freedom to you. You have to be clear in what you mean by height of tree. Okay? That being said, the other thing we care about is, like I said, we will try to cache everything in the memory, right? So we want to see how big the tree is if we try to cache everything. So we want to analyze how many pages in total a B plus tree will occupy. And that will translate to this equation right here, which is f1 plus n over f prime. Okay, this should be n. So what is value equal to? Right? So that's essentially what we are trying to calculate, right? And this, there's a well-known formula for this. I'm not going to go to the detail. You can look up the formula to calculate this. And this translates to roughly, actually roughly half of n prime, linear to n prime. And if you consider the leaf level page itself, meaning plus, if you start this formula from n prime rather than from the level above the leaf level page, this whole thing is still linear to n prime, because it's at most 2 times of n prime. In big O notation, is still linear to n prime. So the point is, the total size of the tree is linear to the size of your leaf level, which is good news, right? You don't want to have an indexing structure that's exponential or anything more than linear to your data size. Okay? So here are some examples. Next, here's a simple example. Next, I'm going to show you a crucial difference between how you build the tree. Actually, this explains the experimental results we observed last lecture when I show you the course. I will rerun that experiment today after we learn this concept right here. So there is an important distinction between cluster index and unclustered index. So what I mean by that, so on the left hand side is what we call a cluster index, on the right hand side is what we call an unclustered index. A cluster index, as you can tell, is a tree where your data entries are ordered in the same order as your records. Why? Because the pointers do not cross over each other, which implies that the records are placed into the heap file in the same order as those data entries in the leaf level. Whereas an unclassed index is exactly the opposite. When you sort those data entries, they are no longer in the same order as the records are in the data file. You may wonder, what's a big deal? When yes, I see the difference, but what's really the implication to query performance? I'll show you using an example. Okay. Suppose I'm doing this query, right? All records greater or equal than 24. Translate to SQL. What that means is you select table R, where this attribute is greater or equal than 24. Where A is your search key value indexed by this B plus 3. Does that make sense? And now we are using a cluster index. What happens? Well, you start with the root, and the greater or equal than 24, so you follow this pointer, come to this page, and that's your leaf level already. But keep in mind, your objective is to find the records, not just the data entries themselves. So you cannot stop at the leaf level. You cannot stop here. Does that make sense? You actually have to go down to the data page. So you follow 24 coming down here. And then because it's clustered, records are sorted in the same order as they are in the leaf level. You can do linear scan in your file until you find the first record whose value is outside your range, or you run out of records in this case. So what's the total? One IO to load this page, another IO to load this page, one IO to load this page, and then one IO to load this page, and so on and so forth. And keep in mind, these are also sequential IOs, given the way how we lay pages back to disk, as I explained earlier. So in total, how many IOs you do? 1, 2, 3, 4, 5, 6. You do 6 IOs in total. This is for cluster index. What happened to an unclustered index? The tree looks identical to the cluster case, right? Because whether it's clustered or unclustered, your tree looks identical. Because you always sort the data entries no matter what, and you build the tree. Records are ordered on disk. So for an unclustered tree, this is what you get. You follow this page. You come down here. For the first data entry in the range, you go and fetch the record, which is 24 right here. So it's some record here. By the way, when you finish scanning that record, can you go to the next record and from the heap file and try to load that record and return that to this query? The answer is no, because its hours are not sorted in the same order as they are in the data trees. Which means the next record here may not be a value greater than 24. It could be a value smaller than 24. So what you really have to do is to come back here, look at the next data tree, follow the RID to find where it is, then come back here and continue. So what is the total number I would have to do? 1 per each data entry in the range. 1 per each data entry in the range, which is much bigger than this case. And specifically, So here, I'm going to do this analysis for you, right? So for a range query Q, what is the query cost? For clustered index and unclustered index, right? So for a range query, right? Obviously, in both cases, you have to pay a height of the tree to go down to the leaf level. That's the same for both cases. Whereas in this case, I can then jump to the leaf level, jump to the heap file and start a linear scan over there. The only question left is how many pages you have to do linear scan for. Well, that obviously depends on your size of your query output. Suppose I use K to denote in other words, how many records in the query range from the database, right? How many records are there in the database satisfying you? Then this becomes K divided by B. B is number of records you can hold on a given page. Does that make sense? And of course, to be precise, in the worst case, you take the ceiling of this. Because they may span over, you may have just one record left over that you still need to do one more page break. What is the I/O in this case? Well, you have to pay K I/Os, because if you have K records in the query range, that means you have K data entries in the query range. And you need to pay one I/O for each one of them. So that's K I/Os. But don't forget, load the record, you also need to load the leaf level pages in order to find all the entries. How many pages you have to do for that? Where B prime is how many data entries you can fit in a given page. Does that make sense? Okay, and furthermore, this is typically cached. So you don't have any I/O for these guys. And this is sequential I/Os. And this is random I/Os. So the performance gap between the two is even more dramatic than the numbers indicate themselves. Because sequential I/O is 10 times faster than sequential I/O. So to really compare the two numbers, you have to roughly divide by 10 here to see the difference between the two. Okay? In terms of performance, right? Performance, you scale that by 10. Because sequential I/O typically is 10 times faster than random I/Os. Okay? So that's this analysis, and I will do this experiment with you. So last time I run this experiment, and I will now with the understanding we have today, let's run this experiment one more time. I'm going to use this database, and I want to show query table. As you can tell, these two are identical except that test 1 I have a B tree on reading. On test 2, okay? So the first experiment I'm going to do, so far so good. And each table has about 5 million records, identical records. And the structure is, the schema is ID, name, and rating, right? And rating is the value in the range 1 to 100. And it's uniform distributed. So each rating value has about 5 million divided by 100 number of records. Okay? So 50,000 records per rating value. Does that make sense? Okay. So the first thing I want to do is the rating of ratings. Oh, it's called ratings. Okay. So okay. Yeah. So that's select about 5% of your records. Does that make sense? 5% of your records. So far, so good. So let's run this query and see how long it takes. Yeah. Now I'm going to run the same for test 2. So clearly you see a difference, right? Does that make sense? Yes or no? Yes. Right? Last time we had a little bit glitch in the experiment run. By the way, the difference is actually more dramatic as you would think from these numbers has indicated. Why? Because both of them has to write the output, which is about 250K records. So that a lot of time. So if you don't look at that common cost, the performance gap is even more dramatic, as you can imagine, right? Because it could be that the time taken to write the output is already 0.3 seconds. Then the difference is really 0.01 seconds versus 2.2 something seconds, right? My point is, if you don't look at the common cost of writing data as output, the performance gap is even more dramatic. Last time though, but actually what we're doing here is look at the query. We are actually selecting, we're not doing this, right? What we're doing is this. In other words, you are selecting the data entries. You are not selecting the records. Because ratings, the B plus is built on the rating attribute. For you to output the rating values, you don't have to touch the data file at all. You can serve this query using leaf level pages. So you are essentially selecting only data entries. Now I'm going to run this experiment, the same experiment, but change the query slightly. I will do this. Okay? So what's the difference now? I'm selecting the records, not the data entries. Okay? Much more expensive. Now if I run this with test 2, without index, what will happen? It's actually faster. Why is that? Why is that? The reason is this is unclustered index. When you have an unclustered index, doing a range query for a sizable range, you may end up being more expensive than simply doing linear scan. It makes a lot of sense. Why? Because this value could be much bigger than N over D. because k is the value between 0 to n. But you don't have n pages, you only have n over b pages. And these are sequential IO as well. When you do a linear, when you operate, it's a sequential scan IO. Which means, really, you are comparing this value against this divided by 10. Whoever is smaller will be the winner. Does that make sense? In our case, this k is roughly 250k. So that shows you the subtlety in using indexing structures. Does that make sense? And another observation is the reason that this time you run this query. We'll run this query one more time. First run of this experiment is faster than the first time we run this experiment. The first time we run it is 2.5 seconds because when you have no indexing structure, see like this versus actually it's the same, right? When you have no indexing structure, the cost should be the same because you're linear scan the records. Why there's a difference in running time? Well, because you have buffer. Okay? Does that make sense? In fact, what I'm going to do is I will here. So this command is used to clear the cache, clear all the buffers. Right? So now if I this query, okay? Remember just now is what, 1 point some seconds, right? I think this will become back to 2 point some seconds because I cleared the cache. But let's see whether that's the case or not. Okay? Do you see the effect of the buffer? That's because you have a buffer inside DBMS that's caching some of the records.
So if you run it again right now, what would it be?
It will be 1 point some second, I'm sure. Okay? So there are all these little tricky system issues. So this reminds you that writing code for a system is not simply about writing code. You really need to understand the interplay of different system components in order to come with the best performance. Question? I think he was first.
So could the query planner realize in certain conditions not to use index then?
That's a very, very good question. And let me repeat the question. The question is, can the query planner figure out automatically that when I do this over test 1, when I do this, I should not use that uncluttered index, but I should just go linear scan. But when I do this, I better use my index. So that's the question, right? So this has to do with something called CBO, which is obviously, why it's called CBO stands for call space optimization. Why I say this is, if you think about it, the reason that in this case you don't want to use that index is because your range is so big. But if your range is small enough, it might still make sense to do this rather than do linear scan. So you cannot simply look at the structure of your query and say, oh, whenever you select records and you have an uncluttered index, you should not use that uncluttered index. That's not necessarily the case. It really depends on the actual cost of your particular query, right? Even for the same structure of your query. So this is called CBO, cost-based optimization. And this has to do with a profound topic that we will talk about later on. It's called selectivity estimation. Essentially, if you can estimate these numbers, then the planner can make a decision, right? I can do a rough estimation. You have a 10 here, then compare the two values, and I can kind of tell which one is a better choice to go with. But even if you do that, you still didn't cater for the case that some pages might have been buffered in your buffer, right? But still, even without that, I can get a rough estimation which is better, which is worse. Obviously, MySQL that. There's a reason for it because MySQL is purchased by Oracle, and Oracle obviously has the incentive to make MySQL not as good as Oracle. Otherwise, nobody's gonna use Oracle, right? So it's not surprising that the core optimizer of MySQL doesn't do a good job here. I think if you run the same experiments on PostgreSQL, the query planner actually will tell the difference. Okay, you guys can actually go and try this on PostgreSQL. In fact, you can explain to see which one the query planner gonna end up with. And later on, when we come to the query optimizer part, if time permits, I will run this same experiment on PostgreSQL to convince you that PostgreSQL actually, the query optimizer of PostgreSQL actually does a fairly good job. Not as good as Oracle, but fairly good. MySQL is not very, in this case, not very good. Okay, as we see from the experiments. Okay, now coming back. Now we know why that query becomes so expensive because you are doing essentially these things. That's why the second query on test one table becomes so expensive because you're doing a lot of math. Finally, I want to mention that in addition to cluster index and uncluster index, there's another alternative called cluster file. A cluster file is nothing else but a cluster index with alternative 1 for its data trace. So recall, what is alternative 1 for a data tree? It's simply the record itself. That makes sense? The record itself. Okay? So a cluster file is a cluster index with alternative 1. What that essentially means is you no longer have these levels. Your leaf level is your data file. Imagine you don't have this level at all. The root level, in this case, the root level index those pages in the data file directly. And if that's the case, that's called a cluster file. Does that make sense? So it's a special cluster index. The final remark I want to make is that for a given table, you can have only one cluster index. Why? Because you record can in one fashion. You only have one fixed order of your records. But you can have as many uncluttered indexes as you want. In fact, by default, in MySQL database and in a lot of database systems, the default is you always build a cluster index on the primary key of your table. A primary key on your table. A cluster index on the primary key of your table. Okay. So that being said, that's why the rating, the B+3 on ratings by default must be an unclustered index because you can only have one cluster index, obviously, because it can only be sorted in one order. You cannot have records sorted both by ID and the ratings. Impossible. Unless you are willing to duplicate your record once more. But duplicate your records introduce storage overhead, but more importantly, introduce update and insertion anomaly, because now you have to update and insert in two places. And over time, it becomes hard to keep consistent values in the two copies. Yes.
That's only when using alternative 1, right?
No.
Because if you use a different
If you use whatever alternative, you can only have one cluster index. right? Because record can only sort it on one order. That's the fundamental constraint. That's the fundamental constraint, right? Okay.
But couldn't you like during the record IDs? Couldn't you duplicate them and sort the record IDs in different ways?
Well, no. You sort in the data entry in the leaf level page. You sort by data entries, right? So there's only one way of sorting your data entries anyway. Of course, the only way you can change that is you can build multiple trees with different search key value. For example, I can have a rating B plus tree, I can have a grade B plus tree, I can have a name B plus tree. And these can sort by different orders, rating, name, and grade, respectively. But no matter how many such B plus tree you build, at the end of the day, your records can only be sorted in one fashion. So only one of them, or even sorting in the same order as your record. That's why you can only have one class index, but you can have as many unclassed index as you wish. Okay? So all that being said, I'm gonna talk about, so here is a typical, here are some typical values of B plus tree that I can convince you that it is possible to cache the first two levels for the most part. Okay? So let's say the typical order is 100. What's order, by the way? Order is the terminology we use to quantify this value. And this is called the order of the B plus tree. Half capacity of your page is what we call the order of your tree. Half capacity of your tree is called the order of your tree. Why we do that is because when we do either bar coding or when we do dynamic reorganization of your tree, one fundamental requirement is that the fan out of your tree, meaning any page, how many entries you have on that page, cannot be too small. Because in the extreme case, if it becomes so small, it degenerates to a binary tree. A B plus tree degenerates to a binary tree where you fan out essentially equal to 2, which is one entry plus the leftmost pointer. So the fan out is 2. Does that make sense? By the way, using that definition, your fan out should be plus 1, right? You have the leftmost pointer to cater for. So if you don't have any constraint, in the extreme case, I can degenerate a B plus tree to a binary tree, but that's a waste of your space because essentially you are using a whole page to store only a single value. The entire page is empty. Then you're paying an I/O for nothing, if you think about it. You're paying all the expensive cost of reading a this page, but only to retrieve a single entry. That's too expensive. For that reason, people design this constraint that for a B plus tree, the fan out must be at least half of the capacity of your. Translate to this I/O operation. What that means is each I/O is meaningful to do. It's worthwhile to do I/O because you're loading at least half of the capacity of the page. Okay, except you don't have to enforce this constraint for the root level node because the root maybe you only have one entry left. And you have to have a page for it. So you cannot enforce this constraint for the root level page. Okay? So except for the root level page, all the other pages, index page and the leaf level pages, all included, must satisfy this constraint right here. And this is what we call the order of the tree. The typical order, let's say, is 100. Meaning the max index entry and data entry is 8 bytes. Integer search key value plus pointer, that's 8 bytes. 200 max capacity, that's only what? That's only 1.6K. Your page size only needs to be 1.6K to have an order of 200, which is fairly common, right? Typical page size is 4K or 8 kilobytes. I think for simple DB is 4 kilobytes, the page size, right? So order of hundreds is fairly common. Actually, it's very conservative. Typical order is bigger than 100. And let's say I set my utilization ratio. Another word for that is called fill factor. How much you fill into a page. To 67%, 2/3. Okay? Which translates to 200 times 2/3. That's about 133 entries per page. Using that setup, how many records I can index using 4 levels of my tree. 4 levels of my tree. With only 4 levels, I can already index 300 million records. With 300 million records, found out of 133, my tree is only of height of 4. So in 4 levels, I can index all of them. And in this case, if you do the math, the level 1 only 1 page. Let's say I've used 8 kilobytes page, only 1 megabyte. Even if you go all the way to level 3, that's only 133 megabytes. So, which means if I cache all the first 3 levels, except the last level, which is the leaf level, I'm only using about 134 megabytes of my main memory, which is nothing in today's server machines. So that basically explains the argument I made earlier. Typically, the first few levels of repository are cached in buffer because they are small in size anyway. That makes sense? So this is what this analysis is about. Now, finally, let's talk about insertion and deletion in repository. Okay? The objective you see in the static case. So first of all, let's look at the insertion case. Then we talk about the deletion case. Keep in mind, your goal is very simple. Your goal is to make your tree balanced all the time. Okay, that's the objective. And of course, the other objective goes without saying is that you maintain your tree balance, and at the same time, all the entries are still in sorted order. Because you can easily make a balanced tree without maintaining the order, but then it's meaningless if you do that, right? So you want to maintain a balanced tree with data entries in order. That's the objective. How do you do that? So the assumption here is I'm going to assume that the current record has been inserted into the data file. So I don't worry about that. So my objective is really to insert the corresponding data entry. So I have a data entry, so PK, and I have RID, and I want to insert this into the tree. So that's my setup. Okay? I don't care about how your record is inserted. I assume that's taken care of already. So it's inserted into the data file somewhere. So that insertion depends on whether it's a cluster index or unclassed index has different costs, obviously. But we talked about those details before, right? Inserting into a solid file, inserting into a heap file. The difference, we explained those before, right? So assume that's taken care of, and all you need to do is insert into my debug string. Okay? So the first step I do is I find the corresponding leaf node that this data entry should go into, which is the line number 1 here. This is nothing else but doing a search using this search key value k. Right? I do a search to find the leaf level page L that this search key value k should go into. If that leaf level page L has at least 1 space left, 1 data entry space left, then I'm done. I place the data entry into that page. Of course, make sure it's in order, but that's easy, right? By this time, operation. Because I load the page to the buffer, I simply want to make sure I update the page in a way that the data entry, this new data entry goes into that page in order. That's easy, right? There's no I/O involved at that point. So if you have space left, fantastic. Very simple. You're done. You return immediately. You basically pin this page to the buffer, update the page, and mark the page dirty. And sometime later, the buffer will write this page back to disk. When the page is to be replaced, the buffer will write the page back to disk first. Okay? So that's the update operation for this. The tricky case is this page is entirely occupied. It's completely occupied. There's no space left whatsoever for another data entry. How do you do it? Okay? So that's the question. So I'm going to show you how to do that next. So imagine we zoom in to that page. We zoom into that case. Okay? And when I zoom in, I'm going to look at the page. This is the index page. There is an index entry that points to this. Okay? So When I zoom in, the picture looks like this. And then I'm going to have two pages to the left and right at the leaf level of the page I'm trying to insert this entry into, right? So that's a picture I have when I zoom into this particular case. Do you follow me? Yes? So the one default option you do is to split yeah. So what you do is you split this page. So I have no space here, right? So what I'm going to do is I'm going to introduce a new page. So there's some entries here, some entries here, as you can imagine. Maybe full, may not be full, right? So these pages may not be completely occupied, but they could be completely occupied. So the picture I'm going to do is I'm going to introduce a new page. This is L. I introduce a new page called L1. That's completely empty. Okay? I ask my DSpace manager to allocate a new page for me. And what I'm going to do is I'm going to update this pointer to like that. Okay? And that's what I'm going to do. And then I'm going to take all the entries from here plus this new entry, all these entries plus this, I'm going to redistribute them into this page and this page. Altogether, how many entries in total you have? Well, suppose order is D, right? Order is D, so the max capacity D prime is essentially 2D by the definition of order, right? And how many entries I have in this case? By the fact that this is completely occupied, you have this many entries to begin with, plus now new entries. So you have 2D plus 1 entries. And you distribute that into two pages. So what are some possible balanced distribution? Well, you can either do D or D plus 1, or you do D plus 1D. Right? So those are two possible distributions of those keys. Of course, in order. You sort them, then you put the first D entries into one, then the next D plus 1 entry into another, or you do D plus 1 into the first one, and D entries the remaining D to another page. You follow me? Which way you do in practice doesn't really matter as long as you are consistent in the way you split, right? If you do a D plus 1 split, you do that all the time. You don't alternate between the two. Let's say we use this. So what the picture looks like is going to be after the split, it will be something like where this entry goes, well, I don't know. It depends on the special value of the search key K and the existing value for the search key of those entries in the original page. So this could be here or here, depending on where you are in the sorted order. Doesn't really matter, right? It goes either to this page or this page in the sorted order of all these data entries. Okay? So far, so good. Yeah, question?
Sorry, what would be the value of D exactly?
D is order. Just explain, right? That's half of the capacity of your page.
Gotcha.
Alright? That's the maximum capacity to D. Okay? Good question, good collection. If you have any clarification questions, just ask me anytime, okay? Alright, so far, so good, right? But one thing we haven't done yet is if you look at this page, what it looks like. Well, what it looks like will be something like that. It indexes all the leaf level pages. What's missing here is you don't have an entry for this newly created leaf level page, which obviously is not okay, because if you leave the tree like this, nobody can ever find this page here, because upper level don't even know the existence of this page. So you have to fix that. How do you fix that? Well, think about the park loading process. What we do? Yeah.
I have a quick question.
Yes.
So say if we don't, so right now there's no pointer to that new page, is that essentially the same as just having an overflow page?
Essentially the same, right? Because you basically have to go down here to find it. And as you keep doing this, essentially this dark region become longer and longer. You end up doing a really expensive scan in the leaf level. But very good observation. Okay. So we need to fix that. Okay. So how do we fix that? Well, the idea is, think about what we have done in the bar coding process. What we said is, for each leaf level page, we take the smallest search key value. So we take this key value out. Let's say this key value is k prime. So we take this k prime is not necessarily the same as this k. It's basically, it could be that k, because if it happens to be the smallest search key value of the second page, then yes, it is that key value k. But typically it is not, right? I use k prime to denote that smallest search key value from the second page. So I make an index entry out of it with page ID. So this pointer essentially is the page ID of this new page. So that's essentially just a page ID. Then I will try to place this entry into that level above. That index page in the level above. Do you follow me? At this point, one of the two cases is going to happen. Either this index entry has space, this index page has space, then that's easy. You basically, what you're going to do is move this entry to here, and you place this k prime here, and you make pointer down. So imagine this entry just go there. And you move that entry, index this page backward by one position, then you're done. But imagine if you're unlucky, you don't have space left. So something is already, suppose the capacity is like that. It's 4 instead of 5. Then you don't have space for this new index entry. When you try to place this back into this index page, what happens? What happens? Well, you carry out roughly the same procedure. You basically look at, you coming back here, there must be some level above, and there must be a page next to it. So you carry out roughly the same process over again. You split. Okay? Do you follow me? And this process may propagate. If you are really unlucky, meaning every level you go to, the page is completely occupied. If you are extremely unlucky, then this goes all the way back to the root. You split the existing root page, and you make a new root page. And in that case, the new root page has only what? A single entry. Why? Because there is only one index entry to push to that new root in that case. You increase the height by 1. That also explains why we do not enforce this requirement for the root node. Because root node has to cater for the case of only having one entry to start with. For that reason. Okay? Now, the only subtlety in this whole process is something what I want to explain to you next, which is in the leaf level, when we do a split, we copy the search key value, and we make an index entry for the level above. We make a copy of that value. The reason we do that is this search key value has to stay in the leaf level page because it corresponds to a record in the. So this search key value needs to stay there because it corresponds to an actual data record in the data file. So you have to make a copy of this value when you make an index entry out of it. You basically have to keep a copy of this value in the leaf level. Whereas in the index level, when you do split, one option would be to simply make a copy of the value, like what you did in the leaf level. But as a measure to reduce the number of entries, the less number of entries you have, the more efficient your tree becomes, obviously, right? Does that make sense? So towards that goal, in the index level, we actually do not have to copy the we push the key up. Why is that? Because the index level values are only used to direct the search. They don't really have any concrete semantic meaning as those search key values in the leaf level, where they actually correspond to actual data records. So in the index level, when I do a split, like that, I push this key value. I push this value up. I actually delete it. Actually delete this key from this level. But remember, when I delete, it's actually an index entry, right? Which means it has a key value at a page ID. So what happened is when I push this search key value up, I leave the page ID behind. That page ID simply becomes the leftmost pointer for that new index page. And then I make the index entry like that. So that's the only difference between leaf level split and index level split. Index level split, you push the key value, you push the search key value up because they don't bear any semantic meaning at all. They only used to do direct search. And the fact that you have the space for the leftmost pointer. So instead of leaving this search key value here and occupy an entry space, you remove this search key value from this page, but leave the page ID of that entry there, which becomes the leftmost pointer of that page. So that's the whole insertion process for the vParser. I will show you an example, okay, to illustrate this. So I try to insert 8. So where does it go? It should go to this page here. Do you have space? You don't. So what do? If you don't have space, you will have to split. In this case, what you end up with is 2 and 3 in one page, 5, 7, 8 in another page. Suppose I do a 2-3 split, D and D plus 1. The D in this case is equal to 2, right? D order is 2. Maximum capacity is 4. So we're going to end up with 2, 3, and 5, 7, 8. And you're going to make a new index entry for that second page, which is 5, 7, and 8, which is 5, and a page ID pointing to that new page. And then you take that 5 and new page ID, try to insert into the root level, root page, right? The leaf level, the index page above, which happens to be your root. Do you have space? You don't have space. What happens? You split. So when you end up with 13, 17, 24, 30. Sorry. You end up with 5 and 17, and 5, 13, and 17, 24, 30. So you end up with this is in one page, this is in another page. This 5, where does this 5 come from? That comes from this new page in the leaf level. Okay? So actually, I think, okay? So that's where the 5 come from. Do you follow me? So you place it into this page, and then no space to split. You end up with 5 and 13. With all this problem. So order is 2. You end up with okay? That's what you end up with. And 17 basically points to that page of 19, 20, and 22. And 24 points to that next page, 27, 29, so on and so forth, right? But the point is, in the index level, after the split, when you make an index entry for the level above, you push the smallest key of the second page up. So you don't leave 17 there, you push 17 up. So the page ID originally attached to the entry of 17 now becomes the leftmost pointer of that page, which is this pointer right here, pointing to this page. That's where this pointer come from. It's come from the entry 17 that been pushed up. Okay? So that's the insertion procedure. Any question on this? It does require some, yes?
So when we insert like this, the page with 3 there's 2 spaces left, that will be waste every time because we'll never, if I want to suppose insert 9 and after that 10, so I'll again have to, this way. So again
on this tray,
yeah.
You try to insert 9.
After 9 and after 10, so when I'm doing 10,
If
I'll
you
again
after
have
9 and 10, then you have to split this page.
yeah,
Yes.
but that space will never be used, right?
Which space is never used?
2, 3 after that, I
Oh, yeah. If you, yes, that's a good observation, right? So if you do 9 and 10, the space here is never used. Yes. That bring up is actually the point I tried to make next, which is to counter that effect. So instead of doing a split, another thing you can do before doing the split is what we call borrowing keys, or borrowing space from sibling node. First of all, let me define what I mean by sibling node. A sibling node is a page in the same level with you to the immediate left and right of the current node, but must share the same parent node. With that definition, the sibling node of this node is this one and this one. Must be to the immediate left and right in the same level and share the same parent. So by that definition, the sibling node of this page is only this page, but not this page, because even though it's in the same level to the immediate right, but they don't share the same parent. So before you do split, one thing you can do is to push keys to the left and right instead of doing this expensive split operation. Following your suggestion, if we do insertion of 9 and then 10, what we can do is we can move 5 to here. So this becomes 7, 8, 9, 10. This becomes 2, 3, 5. But if you do that push operation, when you borrow space, you have to push through there. You cannot simply push in the leaf level because you have to update that index entry in the sense that once you push 5 over, 7 becomes the smallest third key value here. So you have to update that entry from 5 to 7. Does that make sense? So that's what we call the borrowing operation. With that being said, of course, sometimes borrowing will fail. If your sibling nodes are completely full as well, then you have to do the split. You have no choice but to do the split. Now, with that being said, I stop right here. Next lecture, I will spend just 5 minutes to talk about the deletion operation. Then we're done with indexing. We will move on to external sorting. But even without deletion, you have everything you know to work on your homework 2. Homework 2 doesn't require you to understand the dynamic insertion, deletion, or reclassification. It only asks you to understand the query cost of different indexing structures. You should start working on homework 2 right away, because I'm going to release lab 2 later this week, definitely before 4 break. So over the 4 break, you have the opportunity to work on your homework 2 and your lab 2. So you want to utilize this time before lab 2 is released to work on your homework 2 as much as you can, so that you can save your time to work on lab 2. Lab 2 is about B plus tree, insertion, deletion, and query using B plus tree. Okay? All right, thanks.